Hello everyone. So today we are going to discuss about the magnetic material. So we will discuss in detail that in transformers or chokes and inductors, what are the fundamental materials uh, by which they are made up of. So let's go. So first material what we use under the inductors, transformers and chokes, it is a core and this is a very important material. So core we have three types of core. Basically one is the alloy core which is silicon steel lamination. So this is also having the 2 3 variety, and then next is the powder iron core, and third is the ferrite core. So silicon steel core, which is called silicon lamination. This is having certain properties for low frequency application, and the good things is that in lamination the saturation flux density is quite high. So this is having two categories, one called CRGO, cold rolled grain oriented steel, and next one is the CRNO, which is non-grain oriented silicon steel, and the initial permeability is also quite high, and this is used for low frequency range. So for less than 20 kilohertz application, we use the silicon lamination. And amorphous metal core is further higher grade than the normal silicon lamination CRGO grade core, and this is a little costlier, and the core loss in this core is less, and the saturation flux density is nearly 1.6 Tesla. The good things is that amorphous core can be used even for up to 100 kilohertz, less than 100 kilohertz frequency application, and still it gives the good result. The core loss in silicon lamination core is high, and the relative cost is medium compared to amorphous metal. The next core is the powder iron core. Powder iron core is made up of the iron powder by mixing with different materials, and the iron powder core is insulated. So the flux density, saturation flux density in this is nearly up to zero point 0.9 Tesla, but we never design any component to the max limit. And the initial permeability varies from 22 to 90, and this is also used for less than 100 kilohertz operation. The core loss in this is high compared to the classes, which are the different classes available under the powder iron core. But the good things is that the cost is very low. Next category under the powder iron core is the sandest core, which is the MSS Arnold. Arnold is the manufacturer. Then Coolmu. Coolmu is the material which is designed by Magnetics Inc. And majority of the core use this material, being that the cost wise it is very low, and the magnetic properties are quite good. So it is nearly the saturation flux density is nearly 1 Tesla. Initial permeability start from 26 to 125, and this can go up to less than 2 megahertz application, and the core loss is medium. Then under the powder iron core, the next categories are high flux MPP core, and the flux density for high flux it's a quite high. It's nearly 1.5 Tesla, and initial permeability is 14 to 160, and frequency which we can use up to less than 3 megahertz, and the core loss is medium and the cost is also medium. MPP is the permealloy core, so the flux density in this is 0.7 Tesla, and permeability initial is 14 to 550 and less than 4 megahertz. The core loss is low and the cost is high. Same way in the ferrite core we have manganese zinc and nickel zinc. The flux density, saturation flux density is quite less. It's max to 0.5 Tesla, and the initial permeability 750 to 15,000. This is used for very high frequency application up to less than 500 kilohertz. The core loss is low and the cost is also low. Same way nickel zinc also have the same properties, similar properties, but this is for further high frequency. This is less than 10 megahertz, and the cost is also low, and the core loss is also low. So next is about the core shapes. So the ferrite cores and powder iron cores are available in different shapes, and the silicon steel cores are in the form of lamination, which we get in the different shapes like EI laminations and other different size in the EI laminations and the U core, C core, cut core, and same way the ferrite core and the powder iron core are also available in the different shapes geometry to fulfill all the geometrical requirements and the design for the magnetic component. So here is the comparison which has been given with respect to their the cost, the different cost involved with each core, like core cost how it is, bobbin cost how it is, binding cost how it would be, assembly cost, cooling how it is if we use this kind of geometry for the core, and shielding. So we have pot core, RM core, EE core, ETD core, PQ core, EP core, toroid core. And very commonly used core are the toroid core, EE core, ETD core, PQ core. And other core also are used depending on your part geometry and part design. So it is up to designer that how you want to design it. So here we are going to discuss about the next material, which is after core, is bobbin. So different core geometry use different shapes of bobbin in different shapes and size and pin configuration. So this kind of bobbin, it is used for EP type of core. This kind of bobbin is used for ETD type of core. You can see the complete geometrical assembly has been shown here. The PQ type of core use this kind of bobbin, and RM type of core used this type of bobbin, and frame and var use this type of bobbin. So bobbin is the plastic materials which is manufactured using the UL grade plastics and the flammability which meets ultimate insulation requirements of the components, and the winding is winded on the bobbin. Next is the bobbin base. So bobbin base, we use the different kind of base which is used to in the different kind of magnetic components. So you can see here this is a toroid base, toroid kind of base, drum base, and then here it is for ET core, pot core. So different bases are available with the bobbin manufacturer, and then they can suggest the best design for one particular core. Next material is the winding material, which is either wire or the foil. It is a magnet wire, and magnet wire, follow certain regulatory standards, which is called NEMA and UL. So NEMA is the National Electrical Manufacturer Association, and this defines that how the magnet wire has to be there. The single, heavy, or triple insulated or quad, and more details you can find out by downloading the magnetic wire data sheets, which will have the electrical specification in detail, and this is how they define like magnet wire 35A, magnet wire 35C. So what kind of coating they have used, polyester, polyamides, and what is their thermal class, and how is the size, it is a round or rectangular, or it is a foil. So different type of winding wires, winding materials are used for different design, and it is up to designer that how he want to choose the conductor. Next is the insulation class for the wire. As I said that there are two major regulatories which define this. It is the Japanese Industrial Standards JIS or ICUL or UL insulation system. So here is the temperature grade for the IEC and their nomenclature, what thermal class it called, like for 105 it called A, 120 it called E, 130 it called class B, class F, class H, and same way the definition is for the UL standards. So this defines the thermal limits of the windings. Next material is the same again, the wire, which here we have tried to show that how is the round wire. So outer layer you can see it is insulations which they put the enamel coating, and inside it is copper which is a pure conductor, and this is how it is available in the market. And you can see that in different size, different gauge, and basically what we use American wire gauge standards for the wire. And the next very important class of wire is the triple insulation wire. So this is having the triple insulations, and when we use this wire we no need to use the additional insulation while winding, but this is very costly, so we need to be very careful while selecting and optimizing our product design and cost, but it can be used wherever it is really necessary to achieve that kind of insulation. Next is the magnetic materials, winding materials, the wire and the foil. So foil are also available in different shapes and size. And here is some kind of details which we try to show that how is the gauge, like this is the dia for round wire 0.9, and for flat wire it will be length and width and thickness. The winding factor, how much can be achieved for round wire, it can be achieved nearly 79 to 80%, but in flat wire it can be achieved up to 94%. And the winding height in this we can go 100%, but in this we can go only 85%. And this is how the section diagram, when you use the round wire, this is how it will look like. And you can see that a lot of unused space are there in this, but in the flat wire, that's what the winding factor we can see here, it is very high. So this can be bounded in better way. Next is the insulation materials which we used between the layers, either different layers on the primary winding between the primary and secondary, and the outer insulation, and then in the pin what kind of tubing we use. So here are the different type of materials which are used for basically transformers, inductors and choke. One is the Meller. Mallards comes this way, and then the layer tape basically from 3M like 1318, 1350F, 92, and then Yahua. Then this is the Teflon tube which is used to separate the tunnels, so winding tunnel, internal, and then the epoxy. Sometimes we use the epoxy also in some of the components, and then the Nomex tape which is used for isolation, and then the margin tape which we used in the side to achieve the creepage and clearance distance, and this is the varnish dot. So this material is really very important. We need to make sure that if our component is the UL insulation system followed component, we need to make sure that all these materials are certified by the UL agency under that particular UL insulation system, and then only it can be used. So with respect to safety requirements, this is a very stringent requirement. We need to see that what are the different ratings for the UL, and if it meets or not, especially thermal ratings, temperature requirements, flammability requirement, etc. And in the actual parts, what is the role of the different materials? Here we have cut one transformer, and the cross sections we try to see that in actual samples how you can see. So you can see that here it is used the layer tape, the winding wire, the core cap, the varnish, and then the copper foil and the bobbin. So you can see all the different kind of materials in the actual parts. And magnetic parts used in real circuits. So you can see that in many applications we use the magnetic component for different application, and here we try to show you one examples of the CT. CT is the current transformer, it is used for current measurement. So this is the schematic, and you can see the real components. And since today we are talking about the magnetic material, so you can see that in actual parts what kind of different material you can identify, like this is a core, this is a bobbin, and this is the tape, Same way, this is the AVR transformer. So AVR transformers are used for different voltage regulations, which you can see the schematic here. And this is the winding schematic which is used inside this transformer. And in this you can see this black color. This is the lamination core, and this is the bobbin used here. These are the, the terminal wires which are used for the end connections. And then this is the base which is used for fixing, and this is the outer tape. And so you can identify that how the different materials play an important role in the construction of the parts. This is some other examples of low voltage power supply transformers, LPS transformers. And this is here the magnetic parts which are used for EMI filter. So this is a common mode choke. Common mode choke is this how it looks like. And then this is the differential mode choke. And thank you very much for watching this video. So we'll meet again with some new different topic. Till then, thank you.